In the next part, we are going to talk about the radius of convergence and the interval of convergence. And the main theorem here is that if you have a power series, then essentially there are just three possibilities. Possibility number one is that the power series converges absolutely for all values of x, right? So in this case, the domain is the whole real line, right? So possibility one is that the domain is the whole real line. Okay. Possibility number two is that the power series converges only at one point and diverges elsewhere. So in this case, the domain is a one element set that consists only of the point A. And possibility number three is that there is a real number such that the power series converges if absolute value of x minus a is less than that number, and diverges if it is more than that number, right? So in other words, what does this mean? So converges if x absolute value of x minus a is less than r. It means that x minus a itself is less than r and bigger than negative r, right? So adding a to this, we get that a plus r less than x less than, sorry, a minus r, of course, a plus r. All right. So this is the interval from a minus r to a plus r, and diverges if x minus a is bigger than r, right? So in this case, diverges. So diverges if x is bigger than a plus r, or x is smaller than a minus r. So notice that when x is a plus minus r exactly, we don't know. So the possibility number three doesn't tell us anything about that. Yeah. So this theorem is, to be honest, it's not very hard to prove this theorem. It is certainly easier than some of the proofs that you have seen in this course. But anyway, the proof is not included. But if you are interested, you can just contact me or just Google it. It's not very hard. Believe me, it's not very hard. So the number r here is called the radius of convergence. Well, in case one, when the domain of the power series is the entire real line, then we just say that the radius of convergence is infinity. And if it is just one point, then we say that the radius of convergence is zero, right? So, and the interval of convergence is just the domain of the function represented by the power series, right? So it is the set for which the power series, set of all values of x, for which the power series converges. Now, notice that this theorem boils down to the following three possibilities. The first possibility is that the radius of convergence is infinite. The second possibility is that the radius of convergence is zero. And the third possibility is when the radius of convergence is some finite number, then basically, depending on whether the endpoints of the interval of convergence are included or not, so we can have like four possible possible intervals of convergence. And usually the question is just to figure out which of the four it is. Yeah? So here is an example. Well, this is our very simple example, right? So here we know that um, the power series, the geometric power series, it represents the function 1 over 1 minus x. So we know that um, it converges when absolute value of x is less than 1, right? So here, notice that the series just contains terms x raised to the power n. So there is no a, which means that a is 0, all right? And this is the same as to write x minus 0. Absolute value is less than 1. And this is, of course, the same as to write that x is less than 1, less than negative 1, right? So, which means that this is our interval of convergence, and this one is our radius of convergence. Okay, now, generally speaking, if you have a question on determining the interval of convergence, then what you need to do is, first, you apply some appropriate test, which usually is the ratio test, or sometimes it is the root test, to find values of x for absolute convergence, okay, and divergence. And you will know the radius of convergence. I'm going to explain how it works in a few seconds, right? Now, once you have figured out what the radius of convergence is, right? So if it is one of the first two possibilities, if the radius of convergence is either infinity or zero, then basically you're done. And if the radius of convergence is some positive number, like, I don't know, 3 or 0.5 or whatever, then you will also need to test for convergence or divergence at the endpoints of the interval of convergence, right? So at the endpoints of the interval of convergence, you just have to start over, and usually the limit comparison test or the alternating series test will help you. Well, here is an example, right? So, okay. Anyway, I hope it's clear with the general method. So, how does it work now? So, suppose that we have this series. So the first step is to apply the ratio test or the root test, right? So this is my AN. Well, and then standard, the printed slides have the ratio test. So let me just, to just to apply the different method to do the root test here. So in this case, both are equally simple, right? So the root test is the following. So you take nth root of absolute value of an. This is nth root of, well, I need to replace this with its equation, x n divided by 2 to the n. All right, so what do I get here? So nth root of x raised to the power n is just x, right? Well, absolute value of x divided by nth root of n times nth root of 2 to the n is just 2. Right? And in the root test, we are supposed to find the limit as n goes to infinity. And the limit as n goes to infinity, so n only appears in this expression, and the limit of nth root of n as n goes to infinity is 1, right? So this is just absolute value of x divided by 2. Okay, and remember that in root test, if the limit of the nth root is less than 1, then we have convergence. If it is more than 1, we have divergence. And if it is exactly 1, it is inconclusive, right? So the root test tells us the following, that our series converges absolutely if absolute value of x over 2 is less than 1, diverges if absolute value of x over 2 is more than 1, and the root test is inconclusive if absolute value of x over 2 is exactly 1. All right, so the first of these possibilities, if absolute value of x is less than 1, it just means that absolute value of x is less than 2. The second means that absolute value of x is more than 2, right? And from these two possibilities, we see that the radius of convergence is 2. It is this number. Okay, and the test is inconclusive if the absolute value of x divided by 2 is 1, which is the same thing as absolute value of x itself is 2. So which means that x is plus minus 2. Right? So to determine the interval of convergence, it remains to check what happens when x is plus or minus 2. Right? So when x is 2, and when x is minus 2. Okay, so if x is 2, it means that we just substitute 2 for x. Then our series is the sum from 1 to infinity of 2 to the n. So I've replaced x with 2 divided by n times 2 to the n. And this is just the sum from 1 to infinity, 1 over n, because these two cancel out. And this is the harmonic series, and it diverges. So which means that x equals 2 is not in the interval of convergence, right? So because the power series diverges at that point. Okay, so now x is negative 2. So if x is negative 2, then our series is the sum from 1 to infinity of minus 2 raised to the power n divided by n times 2 raised to the power n. Same thing, so 2 and 2 cancels out. So this is sum from 1 to infinity minus 1 raised to the power n divided by n. And this is the alternating harmonic series that we already know, and we know that it converges conditionally. Converges conditionally. It probably doesn't matter that it converges conditionally rather than absolutely, but it's just a good kind of thing to remember about it, is that the alternating harmonic series converges conditionally. All right, so which means that 2 should be included into the domain, and minus 2 should, well, 2 is not in the domain, and minus 2 is in the domain. So the interval of convergence is the interval from negative 2, including negative 2, to 2, not including 2. So this is the answer. All right, so here is another method that uses the ratio test rather than the root test. It's up to you which of the two you use here. Both can be applied. All right. So here is the final answer. So the radius of convergence is 2, and the interval of convergence is the interval from negative 2 to 2, including negative 2, but excluding 2. All right. So here is here is the same thing that uses the root test, which I actually explained. So let me just skip. Um, Now, for which values of x does this power series converge? Right. So let me do this. So again, so here we have, this is a n, and since here we have factorials, it is somewhat easier to work with factorials if you apply the ratio test rather than the root test. Yeah, because if you want to use the root test with factorials, then you've got to use the so-called Stirling's approximation. Anyway, so because of the factorials, I will rather apply the root test. Sorry, the ratio test. In the ratio test, I need to find the ratio of a n plus 1 over a n. Right, and the ratio of a n plus 1 over a n is going to be x raised to the power n plus 1 divided by n plus 1 factorial divided by x raised to the n divided by n factorial. All right, so this is the ratio. This is a n plus 1, and this is a n. Okay, so now this is really x raised to the n plus 1 over n plus 1 factorial times n factorial divided by x raised to the power n. Okay, so x is x to the n is cancelled. So this is just x. Well, and then factorial divided by n plus 1 factorial. So let me show it here. So n factorial divided by n plus 1 factorial. N factorial is the product of numbers from 1 up to all the way up to n. And n plus 1 factorial is the product of numbers all the way up to n plus 1. So these are going to cancel out, and the remaining term is just 1 over n plus 1. Right, so this is really nothing else but x over n plus 1. And of course, as n goes to infinity, this goes to 0. Well, according to the ratio test, if this goes to zero, it means that um, the series just converges. Well, converges absolutely. Well, strictly speaking, I should write absolute values in front of all the x's. All right. So that's basically it. So it converges absolutely, regardless of the value of n. So which means r is infinity, right? So the domain of this power series is just all values of x. So which is the interval from negative infinity to infinity, or you can just write it. The domain of this series is the whole real line. All right. And here is example 6. And here we have a power series where the coefficients in front of the coefficients are just n factorial. And you can guess, that probably when you divide by n factorial, then the coefficients are decreasing very quickly. So, which makes the power series converge. And here the coefficients increase very quickly, which will probably make it diverge. But let's figure this out, right? So now again, because of the factorial, so let me apply the ratio test again. So a n plus 1 divided by a n. Well, absolute value. I should write absolute value. This is going to be again, so n plus 1 factorial times x minus 1 raised to the power n divided by n factorial times x minus 1 raised, well, sorry, n plus 1 here and raised to the power n here. Well, and again, just like in the previous example, so n plus 1 factorial divided by n factorial is just n plus 1 times absolute value of x minus 1. Right? And the question is, what is the limit of this expression as n goes to infinity? Right? And notice that as n goes to infinity, so we have this coefficient n plus 1 here, which just grows, indefinitely. So the answer is infinite. Right? And if the answer is infinity, it means that the power series diverges. Well, essentially, it diverges for all x, but there is an exception. So when this term is exactly zero, then our ratio is just zero. Well, strictly speaking, it doesn't really make sense because this will be the ratio of zero divided by zero. But when this term is exactly zero, it means that our power series is just a series of zeros, and then of course it converges, right? So which means that essentially it diverges for all x except for the only value of x when this absolute value, when this box term is zero, so which is x equals 1, right? So it diverges for all x except for 1. And here we have the second possibility when the domain of the power series is just one point and the radius of convergence is 0. All right, so the interval of convergence is just 1 point. It's not really an interval per se, and the radius of convergence is 0. All right, so that's all about the radius of convergence and the interval of convergence.